Welcome to the GaN Talk podcast, brought to you by EPC and hosted by Maurizio Di Paolo Emilio, Marcom Director at EPC. This show brings to life the stories behind GaN technologies and products. In each episode, you'll hear engineers, executives, and academics share insights on the challenges and opportunities shaping the GaN market. Here is your host, Maurizio Di Paolo Emilio.
Hello everyone, and welcome to this new episode of GaN Talk podcast, where we will talk about low voltage GaN, the next frontier in power semiconductor. So today we are joined by Paul Pickering, Research Director at Omdia and a leading analyst covering the global power semiconductor industry. Paul tracks power devices trends such as GaN and silicon carbide technology closely, as well as market forces driving applications ranging from AI data centers, industrial automation, to electric vehicles, robotics, and so on. So we will talk about how low voltage GaN is changing the face of power electronics, so the opportunities opening up in AI power conversion, and what's in store for wide bandgap semiconductors. So, hi Paul, welcome aboard, welcome to the podcast. It's a pleasure to have you on. How are you? How's it going?
I'm great, yes. Thank you, Maurizio. It's great to be here.
Thank you. Where are you located, Paul?
I am located in Arizona, United States, so it's very hot right now.
Yeah, I can imagine. Good. So, let's start. I have a couple of questions to share with you. Let's start talking about you. Could you briefly introduce yourself? Tell us more about your role, your company's strategy in the GaN power semiconductor market.
Yeah, glad to. I'm Paul Pickering. I'm a research director at Omdia in the semiconductor team. I manage a team of semiconductor analysts who cover power, industrial, automotive, MCU, and several other things too. So as a market research company, our job is not to really have a deep dive on the technology and the development. We follow the market. We provide independent market intelligence, track things like global capacities. And as you mentioned earlier, we track forecasts and trends in different areas across the entire landscape, which of course includes GaN, the subject of our discussion today, and also SiC and silicon, which I'm sure we'll mention in the discussion today. So that's what we do. So I'm looking forward to having a discussion with you on future prospects for the GaN, particularly the low voltage GaN market.
Great. Thank you, Paul. So indeed, the industry has recently seen the introduction of GaN solutions, GaN transistors rated below 40 volts. In particular, I can mention our product EPC 23778 at 25 volt. So the question is, how do you expect low voltage GaN devices 40 volt and below to change the landscape, the competition, the competitive landscape for power transistors? So which applications do you think will be disrupted first?
Yeah, I think low voltage GaN below 40 volts, as you mentioned, has potential to be one of the most disruptive developments we've seen in recent years. Historically, as you know, GaN has been associated with higher voltage applications. Fast chargers is the case in point. And automotive power conversion, OBCs, is another one where GaN has been making inroads. But now, once we start moving into the 48 volt and below 48 volt devices, we are competing directly with markets that have long been dominated by silicon MOSFETs. And the GaN value proposition is well known. Higher switching frequencies leading to smaller passive components, a lower weight, greater power density. And, for some of these applications, the system level benefits, the reducing the size of the inductors and so on, can be just as important, if not more so, than the individual performance of the transistors. So from that standpoint, we expect that one of the first things that's going to be affected is battery-powered applications, because size, weight, and battery life are all critical in those. Drones are a case in point, and I know EPC is put a lot of emphasis on drones because increasing efficiency translates directly into increased use of the battery, which leads to longer flight times or increased payload. Another interesting application is going to be humanoid robots, which is something that got an awful lot of attention at PCIM just last month, because that has very many motor drives that are packed into a very constrained space. And then also we could talk about other applications where similar constraints apply, cordless tools, e-mobility platforms such as e-bikes and e-scooters. So we look ahead, we see the real competitive shift is not necessarily going to be GaN versus MOSFETs at the device level. As I said, it's going to be integrated GaN-based power solutions that combine several components, the transistor, the driver, protection, control circuitries into a single solution. And that, I think, will be very attractive to customers. And GaN, could therefore become, move into becoming a mainstream choice for battery-powered applications over the next few years.
Thank you. Great. So, talking about the specific features, parameters, so recent low-voltage GaN transistors have surpassed silicon MOSFET in key figures of merit, so including RDS-on, including input capacitance, output capacitance. So why are these parameters so important or critical for AI server and next generation computing platforms?
Yeah, well, the advantages of low voltage GaN are well known, RDS-on, CISS, and COSS, and applications where these metrics result in definite performance advantages. These are going to be very important. AI servers and next generation computing are two of the cases that everybody's getting excited about. RDS-on leads to less conduction loss. AI servers, as we know, are processing enormous workloads, hundreds or even thousands of amps at low voltages. I mean, the latest NVIDIA devices are over 1,000 amps at less than 1 volt. And so any small reduction in on resistance can significantly reduce power dissipation, improving energy efficiency and reducing cooling costs, which cooling costs are a very large part of the total electric bill for a data server. So I believe it's second only to the consumption of the devices themselves. Some of the other ones, input capacitance means it requires less charge to switch on and off, which means that as AI devices, AI systems move to higher switching frequencies, that means we have faster response time and smaller, more compact power supplies. And all this is well understood by EPC and others. And that's one of the big advantages for data centers. Output capacitance, likewise, is reduces switching losses because it means that less energy is stored and discharged through every switching cycle. And anything where we can save energy is going to be a really big deal for the AI, because small improvements in efficiency, 1 or 2% results in a very large reduction in heat dissipated, in cooling costs, and in power consumption in general. So I think that's why GaN is going to be, low voltage GaN in particular, is going to be a really big deal for AI.
So just talking about AI power delivery, how long do you think it will take for GaN to become the preferred technology in high performance solutions, high performance AI power solution, as I mentioned? So what are the main technical barriers or commercial barriers?
Well, I think there's two things to look at here. I mean, GaN, certainly over the last several years, not so much in 2026, but it was in the promising technology stage in AI power delivery. But with recent announcements, such as NVIDIA's well-publicized 800-volt power architecture, that really raises the likelihood of early adoption of GaN. I think over the next 3 to 5 years, perhaps, we're likely to see it become the preferred option in the most performance-sensitive parts of the power architecture. And that is where efficiency, power density, and fast response are the most critical. That said, GaN is still relative to silicon, certainly, and even silicon carbide to a certain extent. GaN is a less mature technology. And when you're looking at some of these markets, automotive is the standard case for AI. It applies also. You find that it's all very well to demonstrate reliability, but data centers want to see reliability demonstrated over an extended period of time. Because one of the things that we are seeing and that we expect is that there's a lot of data centers out there now. Most of them have power supplies in them with silicon carbide, silicon, and a little bit of GaN, which is increasing. But over time, we don't expect that many of those existing installations will be swapping out large numbers of power supplies to install GaN. Where we do expect a big change is going to be where data centers in new builds. That's when, especially ones that meet this 800-volt requirement, those new builds will start from the ground up with new power supplies, which will make an increased use of GaN. I think for low voltage GaN, we're looking somewhere in the 40% year-on-year growth over the next several years. So it's certainly the hottest story in power development at the moment.
Mm-hmm. Good. Very nice. Thank you. So you mentioned also other applications in terms of drones, humanoid, motor control. So GaN solutions are also gaining traction in battery-powered solutions, as you mentioned, brushless DC motor applications, humanoid, drone, e-bikes, and so on. So what about this market in general? So how do you see the next evolution? What level of GaN penetration do you expect?
Well, certainly, I think the initial penetration will be drones is probably the most prevalent application because there's a direct relation between efficiency of the power conversion solution and the payload, as I said, or the battery life. And back in the day, that's why electric vehicles were so quick to adopt silicon carbide, because that was a direct translation between increases in efficiency and increased range. Same thing with drones. Humanoid robots is another one we've mentioned, especially ones that are mobile, which means that they are also battery powered. Some of the others are perhaps not quite as a compelling case. I think GaN will still eventually take over, but certainly if you look at cordless power tools, let's talk about that. I mean, cordless power tools, yes, silicon is well established, but the amount of electronics in a cordless power tool traditionally has been very, very small. In addition, it's very easy in the current ecosystem to replace a battery. Simply you unplug it, plug in a new one, a few seconds, and you're done. So if you have a slight increase in efficiency due to GaN, maybe it's not quite as compelling, especially at the lower price point of a cordless power tools versus, let's say, a drone, certainly a commercial drone, and a humanoid robot. So perhaps it's not be quite as compelling. I think GaN will still win eventually and will start to increase its penetration, but not quite as fast as we'll see in some of these other the drone and humanoid robot markets. I think in addition, another trend, long-term trend in cordless power tools is that they're adding more and more functions around the basic functionality, which is turning something, rotating a drill, right, or driving a motor. They're adding things like geofencing and Bluetooth and all these, right? And so that itself will slowly increase the power consumption and the power drain on the battery, while at the same time, it's not so easy just to put in a larger battery in a power tool, because you run into weight and size constraints. So I think all of these devices will move at different speeds. I think maybe drones might be an early adopter, followed by humanoid robots as they gain traction, especially battery-operated humanoid robots. And then perhaps later on, we'll see things like power tools. And e-bikes is an interesting case. E-bikes, of course, have many of the same range versus power density design constraints as do electric vehicles. So I think that will be another one. Plus, I think in an e-bike, you maybe have a little bit more room to increase the size of the battery and so on. So it's a multifaceted market, I guess is what I'm trying to say. So,
yeah. Thank you, indeed. So thanks for sharing. So cordless tools, as you mentioned, is another market, and every battery-powered solutions, as you mentioned. So talking about EPC, so EPC has been a pioneer in commercial GaN technology for nearly 2 decades. So how do you see EPC? How do you see EPC helping shape the next phase of GaN adoption?
Well, I think since EPC is leading in the low voltage GaN, I think, they will be a key part of what's going on over the next 5 years. As an industry, and this applies to EPC, I think, as everybody else, the industry faces a challenge in replacing silicon in many applications. I mean, if you look at silicon's been around for 50 years. The ecosystem around silicon is very well understood. I mean, if you look at some of the leading silicon power vendors, you will go to the website and you will find massive amounts of information on how to apply, how to design 100 different applications using silicon. And so I think that is the challenge for GaN manufacturers, is to develop that ecosystem, because let's face it, as you know very well, GaN, for somebody who's used to designing with silicon, GaN, a little bit tricky, isn't it? We've got high, very fast rise times to fall times, which means you have to be concerned about parasitics. You have to be concerned about perhaps new types of magnetics to handle these very high frequencies. And so I think there's a big job that needs to be done by the industry, and especially low voltage GaN, because it's the newest kid on the block, so to speak. A big challenge for the industry in developing the ecosystem that makes it easier for people who are not necessarily experts in GaN design to use it, lower the barrier to making GaN easy to implement in their applications. I think another thing that I think is going to be a challenge, and how EPC is obviously involved with, is increased integration. Yeah. We're already seeing, originally it was just standalone GaN transistors, and now we have integrated power ICs that combine the gate drivers with the power IC itself. And now we're starting to see, more recently, protection features and some control functions. And again, this is, to my earlier point, it reduces design complexity, and it lowers the barriers to adoption for customers who may not be experts in GaN. And I'm not necessarily thinking about, the huge customers. I'm thinking about the massive number of people who go through distribution who don't really have the intimate connection with the manufacturer that, say, somebody like Delta Power Supplies, it's a massive supplier like that, can deal directly with the manufacturer. But if you're some person who wants to put GaN to increase your performance, and you build 10,000 units of something a year, it's much more important to capture that, what you might call secondary market, much more important to have a very good ecosystem that helps you incorporate GaN into your designs. So I think it's several different things, but I think really it's all around the ecosystem. And I think that, EPC, as well as its competitors, is something that I hope that, I'm sure your advanced planning people are paying attention to this, to try and bring in more secondary customers who aren't GaN experts.
Thank you, Paul. So this is nice. So we are just in conclusion. We have seen different topics. Let's conclude key takeaways that you would like to share with us in conclusion. Also, sort of looking forward, looking towards the end of this decade. So where do you think we have mentioned different applications? So any emerging application market opportunities that you think the industry is underestimating today, for example? And if you would, what do you believe would be maybe the next major milestone from for GaN technology? You mentioned a couple of things, just key takeaways in 1-2 things.
Yeah, I mean, I think the next, at the top level, the broadest level, I think GaN is right now a sort of a slightly exotic high-performance alternative. And I think GaN has to move, and I expect it to move to being a mainstream power semiconductor platform across multiple markets. And what that will mean, we've already seen it in fast chargers. We're seeing it in data centers. It's starting to happen, automotive systems. But in order to really become a mass market, widely accepted version, I think all of the things I mentioned before, I think the industry needs to do a very good job of helping the customers design in GaN with a minimum amount of unknown design problems, design problems occurring. So that would lead to broader adoption at scale. Increasing integration, I suspect, will be another system, another design feature that will lead to making it easier to use. So I think there will be a rise of highly integrated GaN power ICs with all of the power transistors and all the protection and perhaps some control circuitry. That really leads us to another interesting discussion, which is, once we start integrating GaN functions around the GaN power transistor, will it start to become a potential replacement for silicon BCD, which, as you know, is currently the technology of choice for smart power? And I think, as I understand it, there are some serious fundamental design problems in that happening, so that will mean that a complete GaN smart power design on a single die is unlikely to happen in the near term. What I think will happen will be GaN will integrate many of the functions closely related to power delivery and power protection, and then combine that in a single device, but not on two separate die with the silicon control functions. So I think there'll be a large rise in mixed silicon and GaN products, which will, since some of these co-packaging are becoming more and more feasible, I think that will lead to a GaN taking over some traditional BCD functions. And then finally, vertical GaN is one of the things that, I think a lot of people are looking at towards the end of the time period. Vertical GaN promises that it's going to start bumping up against silicon carbide because it's a vertical topology and you can handle larger amounts of power. So, it's very early, obviously, in that industry. And as you know, there's a lot of talk about it, but not actually a lot of actual products. So I think that's something at the higher level GaN technology we can start to see, certainly over the maybe 2030 or a little bit later. So I think it's exciting times for the GaN industry. I think we're just starting to see GaN become widely accepted as an alternative to silicon carbide. As I said, starting with the higher efficiency, critical applications, and then eventually I expect it to move down into being a broadly well accepted and well understood technology for pretty much every power semiconductor application.
Thank you. Thanks a lot. Yeah, maybe vertical GaN. This is another podcast that we can analyze better some points about vertical GaN. Thanks for mentioning anyway. So, Paul, I say thank you so much for joining us in Talk Podcast, and I wish you a good day and see you next. Thank you, Paul.
I enjoyed it very much. Thank you, Maurizio. Take care.